For illustration, let's consider a simple example of an MDP for a robot trying to walk. In this formulation, we have three states of the robot: a fallen state, a standing state, and a moving state. There are two actions available: a slow limb movement action, which we will call a slow action, and a fast aggressive limb movement, which we will call a fast action. Black arrows shows what happens when the robot takes a slow action in every state, and the green arrows show what happens when the robot takes a fast action. So here, by taking a slow action in the fallen state, there is a 40% chance that the robot will be able to stand up and get a reward of +1. But there is also the 60% chance that the robot will fall back into the fallen state and get a reward of -1. In standing state, the slow action is very reliable. It always transitions the robot to the next state of moving state and gets him a reward of +1. On the other hand, the fast or the aggressive action can earn more reward if it's successful in transitioning the robot to the moving state, but with 40% chance or 0.4 probability, it may make the robot fall and get a reward of -1. Similarly, in the moving state, again, the slow action is very reliable. It always earns a reward of +1 and keeps the robot in the moving state, whereas the fast or aggressive action can earn more reward with 80% chance, but with 20% chance it can make the robot fall and go to the fallen state. Now let's evaluate the following policy. The policy is to take slow action or the first action shown by black arrows in the fallen state, and the fast action or the second action shown by green arrows in the standing and in the moving states. Let's find out the value functions for every state when this policy is followed. So let's evaluate the value of this policy starting at the fallen state, that is V pi f. By definition, this is given by the sum of discounted reward, the expected sum of discounted rewards, that is reward in stage 1, expect immediate reward, plus gamma times the reward in stage 2, plus gamma squared times the reward in round 3, and so on, given that the starting state is the fallen state f. For starters, let's take gamma equals 0, so that the value of the policy starting in state f is simply the expected immediate reward, given that the starting state is the fallen state f. To compute the immediate reward, let's look at the two possibilities that can happen for the next state. So the policy says that starting from the fallen state, the action taken has to be the slow action, in which case with 0.6 probability the next state is again the fallen state and the reward is -1. With 0.4 probability the next state is the standing state and the reward is +1. So the expected immediate reward is 0.6 times -1 plus 0.4 times +1, that's -0.2. So this is for gamma equals 0. We see here it appears that the robot should not try to stand up because it's getting negative reward as a result. But this is because we took gamma equals 0, which means that the goal of the robot was very myopic. No importance was given to the future rewards of standing up. Let's say now that the gamma is non-zero, say 0.9. And now evaluate the value function again. Now we have to evaluate these other terms, higher order terms. Let's look at the second stage reward, that's which is expected value of R2 given S1 equals F. To evaluate the second stage reward, we have to now expand this tree further. If in the first stage we move to the fallen state, then there are two possible scenarios. The policy will always take the slow action in this state. With 0.6 probability, it will go back to the fallen state, and with 0.4, it will go to the standing state and earn a reward of +1. In the standing state, the policy always takes the fast action, which makes it go to the fallen state with probability 0.4 and to a better moving state with probability 0.6. The reward is +2 in the last transition. So the expected reward now can be computed for the second stage as with 0.6 goes to fallen state, earns reward of -1. With 0.4, it's +1. Then from the standing state with 0.4 probability, it goes to fallen state to get a reward of -1. But with 0.6 probability, the reward is +2 when it goes to moving state. So the second stage reward, if we compute this, it's just 0.2. So we have the second term in this expression, so that the value function can now be written as the first term, which we computed previously as -0.2 plus gamma times the second stage expected reward, which we computed as +0.2, and then further terms 3 and so on. So we can already see that if gamma is close to 1, then the reward of or the value of trying to stand is not negative. If we really wanted to compute the accurate value function, we would have to evaluate the further terms. For example, evaluating the third term, we need to analyze 8 possible scenarios from these nodes. So we can see that the brute force evaluation of value function quickly become very tedious, as we have to evaluate for a tree of possibilities. And here we were just evaluating the value function of one policy for one state. This is where Bellman equations become useful. Bellman equations, named after their discoverer Richard Bellman, provide a recursive formula for evaluating the value function. The idea is to decompose value of a state in the expected immediate reward plus the discounted value function of the next state. It's easy to derive this formula, so let's do that quickly. By definition, we know that the value of a policy in a state is given by the expected sum of discounted rewards. That's the reward in the first round plus gamma times reward in the second round plus gamma squared times reward in the third round, and so on. Expected value of this, given that the starting state is S. Now let's decompose this into two terms. The first term just takes the R1 here, that's expected value of R1 given S1 is S. The second term takes the rest of it, so taking the gamma out, it's R2 plus gamma times R3, so on, given that S1 is S. Now the first term here is nothing but the expected reward in the first round given the policy pi and state being S, so that's R of S pi S. And the second term is in fact the expected value function in state S2 given the S1 is S. Now, since we know the distribution of S2, it's given by the transition probability matrix P, we can also write this as for all possible values of S2, the probability of second state being S2 is given by the transition probability matrix times the value of policy pi in that state. And that's exactly the recursive expression that we have for Bellman equations.